Hello, Fusion fans. Dr. Matt Moynihan here. Wanted to do a discussion of Todd Rider's 1995 thesis and paper, Fundamental Limitations of Fusion Plasma Systems Not in Thermodynamic Equilibrium. So this is a bear of a topic. I'm just going to say that up front. You should settle in for a long talk here because this one is a very difficult topic. It's a bit of plasma physics and theory that has major implications for a whole class of fusion reactors. And it was a big fight that happened between a bunch of plasma physicists in the 90s that you will uncover as you're doing research on fusion reactors today. And I'm gonna go into it, but it's a broad topic, and I'm gonna focus on his 95 paper. He also wrote a thesis, which I'm not going to go into as much detail, but it's a broad extension of the paper that he wrote specifically on the Polywell. Anyway, so I hope you're prepared for a bit of a plasma theory that's a pretty esoteric topic, but I'm struggling. I want to make this a palatable, simple way to understand this paper and follow along. So we're going to be following along closely with the 95 paper. And it's almost like if you're in graduate school, you might remember Journal Club. This is my Journal Club presentation on Todd Rider's thesis or his work. Okay, so let's provide some background on the work. The whole story begins with Robert Broussard, actually in the 1980s. And Robert Broussard proposed something called the Polywell, which was a specific idea where you would trap a bunch of negative plasma in a cuss trap, and that would suck in ions to undergo nuclear fusion. So I have issue with the Polywell, and that's addressed in two separate videos that I will point you to. But Broussard proposed this in literature, and he also proposed the idea of adding sound waves to enhance the trap. And both those ideas were picked up by MIT in the late 1980s, like 89, 90. And the person who picked them up was a guy named Larry Linsky. Larry Linsky was famous in our community. He was a professor of nuclear engineering. I think he also had a joint appointment in the Department of Plasma Physics. But he was famous in our community for writing The Trouble with Fusion, which was a widely read article in the early 1980s, 83, that criticized fusion, the entire field, and went out to the general public and was read by members of Congress, resulted in Larry going in front of Congress and giving congressional testimony on the state of fusion. Ultimately, that resulted in budget cuts. We had serious budget cuts in 86, 87. Which chilled our field for about a generation, actually. So Larry Linsky is well known inside the fusion community, and he was a professor of nuclear engineering. He was a fusion guy, I think, early in his career, but then came to the conclusion that it wasn't viable and switched over to small modular reactors and nuclear reactors. So he switched late in his career to nuclear reactors. So he's the critic, right? And he's the professor at MIT. He's the one who first reads Broussard's paper and says, I think this is an interesting idea to analyze from a theoretical perspective, because I'm a theory guy, and I've got the perfect person to do that, and that is Todd Rider, who was just then entering graduate school at MIT to study nuclear fusion. And Todd Rider comes in all bright-eyed, bushy-tailed, super excited about the Polywell, believes that it's going to work. And his specialty is math. And that's mostly what this paper is. It is a math-heavy paper. Not modeling, just math. And the math are all back-of-the-envelope theory calculations that, if we did this today, we totally wouldn't do it this way. We do simulations. Oh, just one other thing to add about Larry. He was quoted as saying that he was trying to get these problems voiced within the academic community internally, and he was basically repressed, and he couldn't make that argument. So instead of trying to fight his own academics, he went out to the general public. The trouble with fusion was geared and targeted towards normal people. And that's how he was able to voice all these issues. And he found a welcome, receptive Congress to help him out. So anyway, going back to Todd Rider. Todd Rider, super excited. He's a math guy. He's going to do a lot of math to solve and answer these questions about the Polywell. And his paper eventually touches on another concept called the penning trap system, where they try to make a negative plasma using penning traps. Okay, so he's going to do both systems. And as they said, he was super excited when he started, but eventually he comes to the conclusion it's not going to work, and he eventually kills it. And after that, he leaves fusion entirely and goes into human health. And today he's got something called the Rider Institute, which is in Boston, and they have a method to eliminate diseases called Draco. And you can go online and read about this. It's a pretty exciting thing. You know, it's like Rider, if he's going to do something meaningful for mankind because he's a smart guy. And if it's not going to be fusion, I guess it's going to be, human health, right? So, and there's a couple other key players in this saga that we're going to get to, William Nevins and George Miley. But I actually found out about this paper in 97 or 2007, 2008, 2009. I was in grad school by that point, and I was working on ICF, and I caught Robert Broussard's talk at Google about the Polywell and found it fascinating and wanted to learn more about it. So I got all excited. I went online. I logged into Talk Polywell and started interacting with the people there to learn more about the Polywell. And very quickly, people were like, oh, you got to check out this Rider work because it's this theory work that argues that the Polywell will not work. And so, being a good graduate student, I went and got the paper, started to read it, and was completely flummoxed by this work. I mean, this was heavy math, heavy theory, heavy plasma physics concepts. It was a very difficult paper to read through. I will attest to that. I think this is a bear of a paper. And I really feel for anyone that's trying to follow along out there. Me personally, it took me at least 8-9 months to get through this paper. And I mean, every night I was reading through it, trying to digest the equations in it, and then getting the reference papers and reading the references. I ended up having to read a lot of references to get a good grasp on the subject. And I wrote 2 blog posts called Explaining the Counter Argument, which I wouldn't recommend you reading. They're written by an amateur at the time. It was me mainly groping through the paper, trying to follow along. But when I wanted to make this video, I pulled out my old copy that was probably, 15 years old. And I read through it and I was like, wow, this still is a bear of a paper. I don't think it's well written. I'll say that up front. I think academics write papers, and a lot of academics can attest to this. You don't have a lot of time, and you just got to finish the paper and get it out, get it published, get it reviewed. And I think that was very much this situation. Rider had to rush through and get this paper out. So it's not the best written paper, and he's not trying to help lay people. I mean, he's writing to his own audience. So he's not really in there to make it clear to normal people what the hell's going on with this work. So anyway, that's my take just up front on the paper. All right, so let's get into a little bit more of the paper itself. There are 2 conceptual frameworks that I want you to have in your head before we start talking about the math and then ultimately the analysis and conclusions. So the first thing is, up front, he splits the paper in half, or actually in thirds. The first third is material that is structure independent. So just a blob of material, a blob of plasma in the Polywell. There's no structure to it. The second half, he adds in a structure, a core, mantle, and edge. So he's treating the Polywell like a big sphere of plasma with a dense core, a big mantle, and then material at the edge. And he's assuming ions are flying in and colliding in the center from all directions. We're going to get to that assumption. That's called convergence, and it's probably not happening. And we'll talk about why. But anyway, that's what he's going to assume. Then the third part of the paper is his results. And his results come in the form of a big chart. They come in the form of a big chart, which estimates all these different mathematical quantities for different reactors, different fuels, different scenarios. And then he also has these plots where he does ratios. It's all ratios in this paper. What's the ratio of fusion rate to X-ray radiation? What's the ratio of fusion rate to energy loss from ions leaving? What's the ratio of fusion rate to scattering reactions? It's all ratios, ratios, ratios. The whole paper is ratios, right? It's all math arguments. I wouldn't focus too much on the chart and the plots. I'll say that up front. Those things are, well, you'll see, they're based on a lot of assumptions. The bigger takeaway is just the key points about the problems that he's finding, okay? And I'll list those at the end. So the focus should be more on the general problems and not the specific numbers, because the numbers can all change depending on, whatever, size, scale, density, temperature, fuel choice, whatever. The key is not so much that stuff. The key is the big conclusions. I think the other takeaway is the equations, which are useful. They can be good rules of thumb. So if you got a plasma, you want to know how it's going to behave, throw in some numbers into Rider's equations and you'll get some sort of, solution that will give you a rough estimate of what you think might happen. Okay? So those are the big takeaways too. And then I'll give my take at the end on what I think about all this. Okay. So, the first thing, let's talk about the structure itself. He envisions the Polywell as having a big sphere of plasma with three parts. A core, which goes about a unit out, so a very small core. And in the core, stuff is dense, materials coming in from all directions, and you've got to model it a certain way because it's because it's so dense. There's like other effects you got to account for. Then there's the mantle, which is a big homogeneous region outside the core where most of the action happens. Most of the fusion, scattering, X-ray generation, ion loss, electron upscattering, etc. Most of the stuff that you care about is happening in that mantle region, and that's anywhere from 50 units to 80 units out from the center. And then there's an edge region where there's not a lot of action. The density is really low. Nothing's happening there. So I'm showing a picture of this core, mantle, edge. That's what it physically looks like. And then if you look at it from a plot of density on the right, you'll see that there's a tight density in the center, and then it slopes out to the edge, and then at the edge it drops off. And he also estimates an effective density across the whole thing for his own purposes. He needs it for a math equation in there, so he throws that in there. He's that slope of density. He's got actually a mathematical description of all this in his paper. So you'll see that all in his paper. It's all written out in equations. Equations aren't the best way to explain things. Most people don't really think in math, and I mean, myself included. I like pictures, so I've translated the equations in the paper into pictures here, so it's easier to follow. So that's the first conception of this reactor. All right. The second conception of this reactor that I want you to have is a model of the ion energy spread. Okay. And this picture that you're seeing here is a bell curve of ion energy, from the left side, which is low energy ions, all the way up to the right side, which are super high energy, hot ions. This picture isn't in his paper, but this emerges from the analysis. If you read it all, you come to the conclusion that this is what it must look like. So when you start ions off at a super high temperature, they collide. They bounce off each other. It's called scattering. And they can upscatter, which is where they get hotter. They collide with something and get hotter. Or they can downscatter, which is where they collide and get colder. And through that process, the energy starts to spread out. you get more and more ions that are colder than the mean or hotter than the mean. And you get that bell curve, that Maxwellian bell curve that is probably pretty common to most people. Most people understand what a bell curve is. Now, in the Polywells case, there's some special caveats to that. First of all, most of the stuff is too cold to fuse. So the bulk of the plasma is too cold to fuse. And of course, this is a time-dependent thing, right? Like at the beginning, it might be tight. At the end, everything's freaking cold and it's all cold. Right. This is sort of somewhere in the middle in that evolution over time. Right. But anyway, that aside, most of the stuff is too cold to fuse. Then there's a cutoff where stuff above this threshold is hot enough to fuse. And so that's the sweet spot. That's the material that's actually undergoing fusion. That's the fuel that's doing its job and creating energy. That's the stuff we like. Beyond that, there is a section of material that is so hot that it fused and now it's gone. And the curve is cut off at that point where material has now fused and it's gone. Because when a fusion reaction occurs, it turns into helium and boom, it's gone from the system. Now, of course, in ignition, there's that special case where they try to get the fusion reaction to stick around long enough to drop its energy back in and reheat the plasma. That's a mechanism for keeping plasma hotter and hotter and hotter. But in this scenario, that Maxwellian curve, the long tail on the hot end is clipped off. It's gone because it's gone. And then there's a brief little section where there's ions that are super hot that upscattered and were escaped. So they scattered and they had so much energy they could escape the trap. And then there's a bunch of ions that are really hot and they're in, quote, useless orbits. They're knocked out to a really far away point in the Polywell and they're rotating around a system where they're not doing anything. They're not even close to the core. They're not dense enough, whatever. This bell curve ties in lots and lots and lots of ideas that come in later in the paper, you'll see. So I wanted to get this up first so you can kind of follow along. And it kind of makes sense. It also, the thermalization thing, we're going to talk about that. Okay, let's move on. There are two big intellectual frameworks that Rider uses to model the Polywell, okay? Because we've talked about the structure and sort of some of the conceptions. Now we need to talk about the math that he's going to use. And the math is based off two intellectual concepts. The first one is Lyman J. Spitzer's work. Lyman J. Spitzer was a professor at Princeton in the 1950s and 60s. He's very famous. He was one of the grandfathers of our field, one of the first generation of fusion plasma physicists. And he modeled plasma starting from an ideal gas. So when you think of an ideal gas, most people have learned PV equals nRT, and you learn that in high school. Ideal gases they're a conceptual framework for what a gas is, okay? And based on some assumptions about what a gas is and how it behaves and what it does, you get a whole bunch of equations that you can use to predict gases and what they do. So Lyman's going to take the ideal gas laws and he's going to say, now I'm going to add a charge. So ideal gas laws are uncharged. Now let's say if everything was charged up and they had a positive and negative charge on it, how would it behave? And this becomes his first image of a plasma. A plasma is a gas that is fully charged. And he writes a whole bunch of math equations to explain that. And he ends up writing a book called The Physics of Fully Ionized Gases. It becomes one of the first plasma physics books out there for fusion that theoreticians can use to understand what's going on. By the way, when this is happening, there's a whole other set of people, most notably Harold Grad at NYU Courant Institute, that are modeling plasma as a fluid that conducts electricity. So Spitzer is, hey, it's a gas that conducts electricity. And a bunch of other people are like, no, it's a fluid that conducts electricity. And that fluid conducts electricity stuff, that becomes magnetohydrodynamics, which you can Google. It's a term, you can look it up. Both, by the way, in 2023, both of these frameworks are super crude. Today we have supercomputers. We can simulate 1 billion particles. We can just create like full-fledged models of stuff. So we don't use these kinds of math equations anymore as much. We can just model the whole thing using particle and cell or whatever. But these things are pretty advanced for 1950s and 60s. Rider's going to take some equations from Spitzer and pull them forward into 1995 and use them to analyze the Polywell. Now, the other framework that he uses is the two-fluid model. And the two-fluid model treats plasma like two overlapping fluids. One for electrons that are negatively charged, one for ions that are positively charged. And both fluids exist in the same volume, the same space. They don't ever touch physically each other. They do interact electrically because they have positives and negative charges. So there's an electrostatic field around the particles, and those electrostatic fields bounce off each other, attract each other, reflect each other, ricochet off each other, whatever. So the two-fluid model is fluid A is ions, positively charged. Now, that fluid is controlled by the Navier-Stokes equations, which control a fluid, and Maxwell's equations, which control electrostatic systems. Then there's the other framework is for the electrons, and they have the Navier-Stokes equations for them and the Maxwell's equations for them. And then there is a third term which covers how ions and electrons interact or see each other or bounce off each other. So two-fluid modeling, it's a way to study plasma, and it's got a lot of flaws. I mean, it's a gross model. It kind of looks at bulk material. It doesn't really dig down and see what the behavior of a single atom is or a single ion. But that's the framework that he's going to use for this model. And by the way, all these equations, this two-fluid stuff, was spelled out in the Naval Research Laboratory Plasma Formulary, which is a little pocket handbook that you can buy or you can get online. At the time, you could get it mailed to you, which encompasses and holds in all these equations. When I got the Rider work, I actually had to go get the plasma formulary. At the time, you had to go on their website, enter your name, your mailing address, and they shipped you one in the mail, which was great. They sent it to you in the mail. So I got my copy in 2009. I had my little pocket plasma formulary, had all the two-fluid model expressions in there and a couple other different expressions for estimating and understanding plasma physics. Yeah, I flipped that book over, and on the back, there was a guy named Joe Huba. I ended up meeting Joe Huba years later. Anyway, so he's pulling all these conceptual frameworks together, and what he gets at the end of the day is a bunch of math expressions that he can use to query the Polywell. And he's going to ask questions like, how long does it take for the ion to fuse? How much fusion rate do we expect? What's the X-ray emissions for a given volume of plasma? A lot of his answers are going to be ratios. Ratio of A to B, B to C, whatever. So you're going to see lots of ratios throughout this this paper. And you're also going to see assumptions. And at the end of the day, right, this is a bunch of math. So math is not reality, okay? The way you do this now is you'd model it, or heck, just build the reactor and try, okay? Because if, as Richard Feynman always said, if you have theory and you have data, and theory's got to be wrong, right? Data is always right. Data is king in science. And so Rider's going to make a whole bunch of theory claims and theory estimations and math assumptions and whatever else, which could all fall apart if somebody just built a Polywell and tested it and said, oh, no, Ryder, you're all wrong, because here's the data that actually shows it in real life. Anyway, okay. So let's get to the assumptions of this. Now, in the paper, there are 7 assumptions, but I've grouped them together into 4 core ones. The first one, so the 4 are convergence, the Coulomb logarithm, quasi-neutrality, and uniformity, which I'm going to talk about uniformity. There's a number of aspects of what I mean by uniformity. So let's talk about convergence first. This is a big one. Okay, convergence is a measure of how dense the plasma gets in the center of this sphere, okay? And in Ryder's work, he assumes that they do converge, and there's a core region where stuff is super dense and hot and flying in from all directions. But almost immediately, he acknowledges that it's probably not happening in real life, okay? And this is going to be backed up by many different pieces of evidence. The first evidence is from another theoretician called William Nevins. William Nevins, at the same time that Ryder's doing all this work, William Nevins is out at Livermore, and he's a senior staff scientist and senior plasma physics theoretician. And he's looking at the Polywell from a different perspective. He's looking at the narrow question of, is it likely that the material, the positive ions are going to fly in and slam together in a point in the center? And he argues no, because of scattering effects. So ions coming in, and even before they get close to the center, they hit another ion, bounce off, scatter away. He's also arguing because of charge effects, the positives and positives rejecting each other, kind of forcing each other apart because of their positive and positive repulsion. And he's also arguing because of upscattering and loss of the well itself. So Nevins argues that things cannot be converged into a point. Ryder's going to assume this with the acknowledgement that it probably won't happen because of Nevins' work. But for his modeling theory, he's just going to assume that it happens, even though he doesn't think it will happen. Now, this kind of fits with, there was a similar thesis done at the University of Maryland in 2016, 2017 that I want to talk about here that's really instructive here. There was a guy named Andrew Chap at the University of Maryland who was hired by Ray Sedgwick to model a somewhat similar problem. Andrew Chap was modeling oscillating beams of ions. And he's got these great videos that I'm hopefully showing one now, which shows ions oscillating through a honeycomb structure, going back and forth, and material is moving through the center region, and it's trying to get dense. And Andrew Chap did this work and argued, unfortunately, that it was impossible to get density high enough. So this isn't the same situation as the Polywell. It's similar, not really the same, kind of the same, sort of. It's a similar situation. It's a situation where ions are trying to fly into the center. Andrew Chap's having the same problem, convergence. He can't get enough material in the center, dense enough to get appreciable amounts of fusion in his simulation. And that was the conclusion of his thesis. He said that this system can't get convergence. And it's kind of similar to what Nevins came to, and similar to what Ryder talks about and kind of comes to in his thesis later on. In general, when plasma is coming into a center region, its positives and positives and negative charge effects limit how dense you can pack this stuff, okay? And that's sort of the conclusion that all 3 guys come to. Now, so instead of a dense point, you get more of a region of space where material is kind of denser, and you can kind of get fusion reactions to occur. I will say that I'd love to see, I bet you that this problem comes up in other systems, and I'll just bring up one. The plasma liner experiment at Los Alamos may have similar issues. I'd be interested to see what their data says, because in that system, they're shooting jets into the center and they're trying to get them to collide at high densities. And I bet you that same sort of situation arises where you got a bunch of ions coming together to a point, and you probably have the same sort of problems that Nevin saw, that Rider saw, that Chap modeled, and that PLX may have experimental evidence for. I don't know. I'd be interested to see some papers from that. I'd reach out to Samuel Langendorf at Los Alamos about that. Okay, so that is convergence. Okay. The next assumption is quasi-neutrality. He's assuming that the plasma is quasi-neutral in a lot of the regions, except for maybe the point in the center where the negative well is created. And then later, he's just going to assume it's quasi-neutral throughout. Now, quasi-neutrality, what does that mean? That means that plasma is happy when positives and negatives are well mixed together. Plasma does not like it when one charge starts to dominate. When you have too much of the negative or too much of the positive, you start getting tearing modes, instabilities, lightning effects. You start seeing plasma suck in charge from surrounding metals or surrounding walls or diagnostics or wherever else. Okay. So he doesn't believe that a negative potential well is really feasible. And that's one of the things this assumption implies. Now, I take issue with this, right? Because the basic rule of the Polywell is that you have a mostly negative plasma, and therefore you can get this effect to occur. Now, I don't know if that's even possible. In fact, I doubt it's possible. I made a video about that. About 5 years after this work comes out, George Miley and Louis Chacon at the University of Illinois come out with a paper arguing that Rider is wrong. And what they do is they say this quasi-neutral assumption you made, Rider, is incorrect because the Polywell is a mostly negative plasma. And therefore, your assumption is incorrect, and therefore all these other things happen that make the Polywell viable, okay? So there you go. There's a bunch of theoreticians having a little theoretician fight between each other. And as a supporter of the Polywell, we would always grab Louis Chacon's and George Miley's work and say, hey, George Miley and Louis Chacon say that Rider's full of it, and he's wrong, and this Polywell thing will work. I personally think the quasi-neutrality assumption is a good assumption because plasma does like to stay relatively in equilibrium. In fact, in 2018, the University of Sydney had a PhD guy named Bowen Reed who tried to make a negative plasma in a Polywell and couldn't really make it happen. So quasi-neutrality, it seems to be sort of more of a law than an assumption. But anyway. All right, let's talk about the third assumption, which is neglecting the Coulombic logarithm in the center core. I don't know. I don't have a really great definition of what the Coulombic logarithm is. It's a measure of plasma behavior relative to density, and it accounts for that. And you see it in a lot of math expressions in there. But Coulombic logarithm is neglected here. And I would love it if somebody out there could really give me a crystal clear definition of what the Coulombic logarithm is. I'd love to see it. In practice, it's a number between 15 and 20 that you can throw into your math that'll kind of clean things up. But what it actually is much more complicated than that. It's a measure of density, effects of density, like as the plasma gets denser, how things are in fact impacted. All right, the fourth and final assumption is a broad assumption about uniformity. Okay, now even as I say that, I want to be a little bit more explicit. Uniformity in fuel density, so not having a concentration of deuterium or tritium, or if it was proton boron 11, boron or proton or whatever, not having any kind of concentration, not having any structure. Okay. Uniformity, homogeneous. The fuel is well mixed all throughout. uniformity in temperature, okay? And later we'll talk about temperature, but having the temperature be relatively uniform throughout the system. Uniformity in energy, having material being roughly the same energy throughout the system. Uniformity in charge, not having any positives or negatives in any one place. Uniformity in direction, not having any directionality to this stuff. So materials flying in from all directions uniformly, and if you go in any direction, the plasma looks the same. So uniformity really across the whole space. All right, so let's start with the analysis. The first bit of analysis, the first thing he does is he estimates the amount of time it takes for an ion to fuse and the amount of fusion energy that's going to be generated from this plasma, okay? And he's going to spit out a math equation. Now, he doesn't really need these things for anything important right now, but what they become is his basis for comparison. What he's going to do now is he's going to uncover all these other effects that are problems, and he's going to take ratios. He's going to take that effect and give it a ratio relative to the fusion rate. And so that comes out, and he'll argue that the Polywell is going to fail because of all these other things. So the first thing is just get a baseline number for how much fusion is coming out and how long it takes for an ion to fuse. And that becomes the basis for comparison. The next chunk is on plasma temperature or ion temperature. So broadly, this isn't exactly in the paper, but broadly, let's talk about this. So in a plasma, in a fusion reactor, there are ions, there are electrons. Of course, the ions are the fuel that are fusing. They're the ones that actually matter. So their temperature matters. The electron temperature does not matter as much because if you make the electrons super hot, who cares? They don't actually do any fusion. They're not actually making any energy, but they're in there. Electrons and ions can have different temperatures. There's a number of examples, of real-world examples of this, where the electrons and ions are different temperatures. And the electrons tend to be hotter because they're smaller. They have almost no mass relative to the ion. Well, I think it's a 1700 or 18, excuse me, I think it's 1780 or 1800 fold difference in mass. And then if it's a deuterium thing, it's like twice as much. Anyway, it's like thousands of times mass difference between the ions and the electrons. So what that means is it's easier to heat the electrons and ions. So what that means is that when you see a fusion reactor, oftentimes the electrons are super hot, the ions are colder. What that also means is that when you see claims by a company that, hey, we got really, really hot plasma, it might be just the electrons that they got hot, not the ions, right? So there are two different temperatures in there. So there's two different populations. There's ions and electrons. They have different temperatures. So that's the first point. The second point is he's going to drill into just the ions. So let's take the electrons off the table for a second. Let's focus on just the ions. He's going to look at the idea of artificially heating or cooling the ions. And the analogy I want you to think of is boiling water, okay? You imagine you got a pot of water on the stove, you're boiling water. The bottom of the pot, the water in the bottom of the pot is super hot, and it's heating up faster than the rest of the pot. So part of the water is hot, part of the water is cold, okay? Now, there's some rate at which hot water is swirling around and mixing together and mixing the pot together and making it all one temperature, okay? And there's an equation for this for fluids, and you can speed things up by mixing or stirring your pot or whatever. In this scenario, it's the same situation, but it's plasma. And in this scenario, a part of the plasma is kept hot or cold. Hypothetically, this is all hypothetical. So Rider wants an expression for energy transfer in this scenario. How fast does energy move from the hot plasma to the cold plasma, or from the cold plasma to the hot plasma, or whatever? Okay. And he's got to do a little bit of math here because he's got scenario 1 where there's a big difference in temperature, so he needs a certain equation for that. Scenario 2, there isn't such a big difference. He needs an equation for that. But anyway, he takes both equations, sticks them in, and boom, comes out with this big conclusion right up front that the temperature can't vary more than 5% across the ions. That's a big conclusion right there. It's a big deal. Is it true for all fusion reactor concepts? No. Is it based on a number of assumptions and back of the envelope assumptions and calculations? Yes. Is it a bunch of math that probably isn't real because data will always override math? Yes. But at the same time, that's the conclusion. Ions have to be within 5% of whatever the mean temperature is. Okay. That's a big deal. It actually has major implications because it hurts the ability to hit a given temperature. Okay. Now, so for instance, when you're fusing proton and boron 11, there is this amazing resonance peak at a specific temperature. If you get all the protons and borons to a specific temperature and you hold them there, you will get fantabulous fusion reactions and huge boosts in fusion energy, tons and tons of fusion coming off. You'll probably make net power. It'll be awesome, okay? Rider is saying here that you can't get everything to one temperature. Okay, it flies in the face of your ability to hit a given temperature because of this 5% variation. And it accounts for, there's also inherent in his math the idea that the plasma is thermalizing. It starts at a hot temperature, and it over time, because ions are bouncing off one another, it starts to spread out into that bell curve. And so eventually, most of this stuff is not hot enough to fuse. Not hot enough to hit that specific temperature. Okay? All right. All right, let's move on to the next sort of set of analysis. Now, the next set of analysis is around the idea of a test ion. He calls it a test ion. He imagines, you can imagine this in your head, a single ion flying into that reactor, into the Polywell. It's going to enter the sphere of material. It's going to move through the edge, the mantle, the core, and then the mantle and the edge, and then oscillate back out on the other side. Now, when the ion does this, it can do one of a few things. It can fuse. It can scatter, both upscatter, where it bounces off something and gains energy, or downscatter, where it bounces off something and loses energy. And if it upscatters, there's an opportunity for it to do two things. It can get kicked into a useless orbit around the outside, or it can get kicked so much that it escapes and flies away. Okay? I think that's like four things: fusion, upscatter, downscatter, or scatter to loss, or scatter to useless orbits. Those five things that it can do. Okay. So he's going to analyze the likelihood of each one of these effects. The way he's going to analyze it is two ways. First of all, he's going to find the characteristic time. So how much time between scattering events or upscattering events. Then he's going to compare that to the fusion rate. And he's going to compare it to the loss rate outside the trap. He's going to come up with a bunch of ratios that'll say it's more likely to scatter than fuse by a factor of 100 or 1,000 against. Or he's going to say, oh, look, scattering rate is higher than fusion rate by some factor. Or loss rate is higher than fusion rate by some factor. These are all gross statistics. It's statistical analysis of large populations of particles in a hot plasma and coming to these conclusions about what's the most likely thing that'll happen. And it's not fusion, unfortunately, according to Rider's work. Again, it's not perfect. Rider's got a lot of assumptions. I'd rather just build the thing and test it. again, scattering is much more common than fusion by a factor of 100 to 1,000. Scattering to loss is much more common than fusion. And there's two caveats here. He adds the idea of electron drag. That's where a positive's flying through a cloud of electrons and losing energy because of a drag force. And he's adding this caveat about background neutral gas, okay? And that's in response to Nicholas Krall's paper on background neutral gas. Background neutral gas, just to back up, there's a population that's fully ionized. There may be stuff in there that's not ionized. And that's probably not the hydrogen or the electrons. It might be something like argon or carbon or oxygen or something else that's not fully ionized. And so you've got to account for a neutral gas. Now, hopefully, you know, these systems are never perfect. There's never a perfect vacuum. So there's always something in there that's not supposed to be there, dirt or whatever. This is an example of that. So he counts for both factors in his ion scattering. Okay, let's move on. Light radiation. Okay, so light radiation is, if you know Lawson, and if you've seen some of my other videos, you know that all fusion reactors lose energy as light, okay? UV, X-ray, IR, visible, all reactors are bleeding energy away as light. And in this scenario, he's going to look at just the X-ray losses. He calls them it's the Bremsstrahlung losses. X-ray losses are a small piece of a larger puzzle of radiation, because there's synchrotron, cyclotron, X-ray, Bremsstrahlung, and there's even other processes that generate light, like plasma instabilities. So bottom line is plasmas bleed light away. He's going to pick a specific subset of that light and look at that, which is just the X-ray losses. So he's got a lot of assumptions here, and I'm not even going to go into detail here because it's probably not worth digging through all this. First of all, he assumes that the plasma is optically thin to X-rays, so he's assuming that the X-rays will get out as soon as they're made. They'll just leave, which is a safe assumption because, you know, unlike the sun, the Polywell is a man-made device, and when X-rays are made, they leave. He assumes that the gas is quasi-neutral, which I have an issue with because that's a basic tenet of the Polywell, that would be broken. And he assumes an isotropic core. Then he has a lot of derivations to do here. I think he adds, it's like 6 things. Let me look. Yeah, he adds 6 different mathematical expressions from different people's work to estimate this X-ray loss equation. And the bottom line is he needs a math expression that predicts how much X-rays are coming off the plasma per square foot. And he starts with Maxton's theory. He adds classical Spitzer theory, a correlation to deal with the Coulombic logarithm, this Dawson modifier. He assumes a couple conditions about the plasma. He assumes that the electron ion temperature isn't very different. So he adds all these expressions together and boom, pops out this expression for estimating the X-ray losses per square foot of plasma. And then he compares that to the power rate, the fusion power rate, and comes to this problem that the X-ray losses are higher than the fusion power rate. I mean, this is really theoretical stuff. I mean, I don't know if I'd buy this. This is not gospel. Definitely not gospel. I mean, with the number of expressions and assumptions and other, you know, add-ons and, you know, wiggle rooms and whatever else he added in, it's not a given. I wouldn't call it the given truth, the God's honest truth that this is going to be true. So I'm gonna be very skeptical here. All right, that's my problem. All right. So let's move on to the next portion of the paper itself, which is the analysis with structure. I'm not going to spend too much time here, but he just assumes that the plasma has a core, a mantle, and an edge. And then he calls an effective density across the thing. And he looks at the idea that Bussard put forward of adding sound waves. So Bussard had the idea that if they added acoustic sound waves to the plasma, it'll increase the density of the plasma. And so he throws in a correction factor for that and says, okay, well, what if that was there? What would that do? And he shows, first thing he shows is that the most of the action that's important is happening in the mantle, not the edge region. He shows that with a nice expression and ratio. And then he talks about electron losses through the cusps. Now, this is where I'm going to draw a line, a hard line. I think he's wrong here. Having studied the polywell for a number of years, the theory of the polywell is that there is a diamagnetic effect that improves the trapping of mass inside the cusp region. And so Rider's work, I think, breaks down here, I would say. He doesn't really understand that and doesn't account for it in his work. So he goes off of expressions that I think would be just wrong for the polywell. His mass loss stuff is just, I don't think it's correct. I don't buy it. I think, if you revisited this work today and you use maybe Lockheed Martin's data on cusp confinement, and maybe someone will do a polywell study and actually measure losses through a cusp, or you could use Joel Rogers' work where he shows that there's a skin current on the outside. Bottom line is, if there's a skin current, the cusp losses are going to be very different than whatever Rider says in this work. I don't think Rider's work is valid here. But, I mean, it's just a portion of his work, right? The rest of it still makes sense to me. So, anyway. Okay. All right. So let's go to his big conclusions here. So the third part of the paper is his results. And like I said, if you go through the paper, it's basically a chart. It looks like an Excel spreadsheet, a chart, where he has different scenarios, different fuels, deuterium, tritium, proton boron 11, at different potential well voltages. Anywhere, I think he does like 60 volts, 600 volts, 400 volts or kilovolts, excuse me. And he looks at what comes out in terms of all these terms that he's laid out. Fusion rate, time to ion scattering, X-ray generation, ion upscattering, ion losses. He's got this big chart. Now, like I said, I don't think we should focus on the chart as much, because all these numbers can change. And again, all this math is back of the envelope kind of calculations, right? This is all this is. It's a bunch of math, not the same thing as experiment, not the same thing as data. But the big takeaway issues are important, I would say. So let's go over what was the important stuff that came out of this paper. Now, the first one is that convergence issue. How well material flying into the center of the polywell or other systems like it can get to high density. Rider, acknowledges up front that that's probably an issue. Nevins elucidates that. Andrew Chap simulates it. I bet you there's data from PLX that backs it up. I don't see, plasma doesn't naturally want to bunch together. Plasma doesn't like bunching together. Space charge issues, positives and positives rejecting each other, negatives and negatives rejecting each other. All this stuff kind of keeps it from getting dense in the center. And so to make a dense plasma in the center, you got to do all kinds of cool stuff, like mechanically squeeze it or compress it or pass it through a magnetic nozzle or a field or whatever. This system doesn't have that kind of oomph to it to make it kind of work. So convergence emerges as a big issue out of Rider's work. The other one is thermalization, right? Having a bell curve in energy is not ideal. What would be great is if you had a bunch of ions that were super hot at one temperature, the perfect temperature for that fusion reaction, and a bunch of electrons that were super cold because they would radiate less energy. That would be the perfect bell curve. And that's not what Rider has here, okay? Rider, this thermalization issue is big. And it also kills the idea that you can hit a specific temperature, like get all the proton and the boron at one specific temperature. The other issue that emerges is mass loss. And that's through the cusps, which as I already said, I disagree with. And then ion upscattering, which is where ions gain enough energy from bouncing off one another that they can escape the trap. Now, ion upscattering, of course, is dependent on having a negative plasma in the center. But the other issue is, I will just raise this now. Rider doesn't consider the skin current thing. The Polywell is supposed to have a current of a skin current on the surface of the trap that may limit ion upscattering as a loss mechanism. And Rider doesn't think about this at all because he probably didn't know it existed. I think it would be interesting to revisit this, the mass loss with the skin current thing going on, because if that exists and it occurs as advertised, then the Polywell may be better at trapping material, and Cuss systems in general, Lockheed Martin's approach, may be better at holding in mass than Rider gives them credit for. And then the quasi-neutrality conclusion is another thing I have an issue with. And then finally, X-ray losses. He talks about X-ray losses as identified as a large problem. X-ray losses, they probably are a large problem because it's hard to see how you can get around them. You know, with the Polywell, you can enhance the trapping with that skin current. You can do some cool stuff with the cusps. You might be able to play game. You know, there's this sound thing that Robert Broussard suggested. Of course, Rider dismisses it. But let's say, you know, there was a scenario where the sound could somehow help the thing. It's hard to see how to get around X-ray losses. I mean, cold electrons will radiate less because they have less energy. And so that might be one way to go. Anyway, those are the big conclusions of his paper. Again, this is supposed to be applicable to a broad class of fusion systems where the plasma is not in thermodynamic equilibrium. And that is a lot of reactor designs out there. Whether it's a specific concept, I'm not going to quibble about because it may not be. And again, as you just saw, there's a lot of holes in Rider's analysis. And again, it's a bunch of theory. Theory isn't data. Data is king, as I said before. Anyway, all right. So let's go to the last portion, which is my particular take on this. I'm going to give you sort of my thoughts at the end here. And even as I say this, I know that some people would disagree with this. My thoughts are that Rider describes a system where the plasma is quasi-neutral. The positives and negatives are well mixed. There's no structure, okay? So like an FRC or a Dynamac or a mirror machine, they all have structure of some kind in it. This system has no structure, and so that's an important distinction between Rider's work and Rider's analysis and what, say, TAE is doing or Helion is doing. Those systems have structure. This has no structure. This thing is also uniform in energy and temperature, in electron and ion temperature, are all roughly close to one another. Although earlier, like I said, the ions are within 5% of one another. The electrons are probably hotter. They can have a higher temperature. But there's a relative uniformity in energy and temperature throughout the system. And then the system is thermalized. That means that material has a bell curve, some kind of bell curve, some kind of curve. Whether you can, whether it's clipped off at the end or what the exact shape is, we can quibble about. But there's some kind of bell curve in energy here. Okay, that's the system Rider's describing. Rider is saying that system is fundamentally flawed and limited. I call that system a blob. And I use that term kind of liberally, but imagine just a cloud of material that's uniform with no structure, no energy distribution. I call that a blob. And Rider is saying that blobs are fundamentally limited. They won't work for fusion reactors. So I accept that conclusion somewhat with some caveats and whatever else. So what that tells me is that we should be designing fusion reactors that are non-blob-like, that are not like blobs at all. They are the most non-blob as possible, meaning that they are structured, that they are compressed, they are squeezed, they are slammed into one another, they are shaped, whatever. Rider's work basically tells us what not to do. And so that's my takeaway from this. Anyway, thank you so much for your time. Hope you enjoyed the lecture. Take care.